So far, we've looked at climate fluctuations on very long timescales, in particular the shift from interglacial to glacial periods and from glacial to interglacial periods. These fluctuations take place on timescales which are difficult to grasp from the human perspective. But particularly in the context of anthropogenic climate change, we would of course like to know how rapidly fluctuations in the climate system can occur. Rapid fluctuations can be triggered at a point in the climate system where we would least expect them, at continental ice sheets. They can become unstable or melt due to temperature increase, and finally a significant amount of fresh water flows into the oceans, for instance into the North Atlantic, and causes the salinity there to decrease. As a result, the deep water formation in the North Atlantic is massively altered. It is weakening. However, deep water formation in the North Atlantic plays a key role in the global ocean circulation, and therefore freshwater input into the North Atlantic can lead to a disturbance in the entire ocean circulation system. This is when we speak of a Heinrich event. Paleoclimate records show us that there have been several of these Heinrich events in the past. These events lasted a few centuries. Compared to the succession of interglacial and glacial periods, these are relatively rapid changes in the climate system. The freshwater influx into the North Atlantic during Heinrich events occurs mainly on a regional scale. But of course we are also interested in the extent to which such a regional influx of freshwater has a global impact as well. For this purpose we use a climate model to test how the model reacts to such a regional influx of fresh water. With this we simulate a large continental ice sheet breaking off and then look at the model simulation to see the regional changes and whether these changes spread globally in the climate system. The following animation shows how the strength of deep water formation and the surface temperature of the North Atlantic Ocean evolve in time. And the first thing we notice in the bottom figure is that there is a rapid change in the strength of the deep water formation. Along with this reduction in deep water formation, the surface temperature of the ocean declines, and the cooling continually spreads to the lower latitudes, that is, towards the equator. This just goes to show that a freshwater influx in the higher latitudes can definitely have an impact on the lower latitudes. Thus, the advantage of such a model simulation is that it can give insight into the temporal development of changes in the climate system in response to such a Heinrich event, which brings a significant amount of fresh water into the ocean. Another question we can ask is, could such a disturbance potentially have impacts beyond the North Atlantic realm as well, for instance on the tropics in general? To examine this, we studied how precipitation patterns in the tropics changed in the context of very weak deep water formation in the North Atlantic, that is, at the end of a Heinrich event. And our graphic shows that a pronounced dipole pattern emerges over the tropical Atlantic, with a definite decrease in precipitation over the northern tropical Atlantic and a definite increase in precipitation over the southern tropical Atlantic. Moreover, we can also see that the precipitation changes are not only confined to the Atlantic region, but rather affect the entire tropics, for instance in the Pacific region, and they can even reach the Indian and Asian monsoon regions. In the end, we can then compare such model results with results from reconstructions, for example from marine sediments.